This is the second presentation about oxidation of sulphide-bearing aggregate, and it focused on test method. So Rodolfo has kindly introduced the topic, which is very good. It saves few slides from my presentation. So maybe I'll go directly into the test method. So this is the work of Dr. Mona El-Musallami, who has completed her PhD with me at Ryerson University a couple of years ago. Her research work was supported by ANSER Discovery Grant, as well as a grant from the Ontario Ministry of Transportation in Canada. So Rodolfo has presented the issue. The issue of sulfide has been worldwide, but it's relatively new to North America. But we had the cases in Trois-Rivières as well as the United States. This is the type of deterioration that we observe in Quebec. And basically, Rodolfo also talked about the mechanism of reaction. And the mechanism of reaction is basically oxidation as well as sulfate attack. So it starts by oxidation to produce sulfuric acid, and then the sulfuric acid form the different type of sulfate attack, whether it's rhyngite, thaumasite, gypsum, or even the solution of calcium silicate hydrate, depending on the severity and the amount of sulfuric acid or sulfate that you produced from the oxidation. The reason the mechanism of reaction is important is because the test method should focus on it. So whenever there is a test method for ASR, for example, alkali-silica reaction, we know that it's a reaction between silica and alkalinity. So acceleration is by promoting or by providing the reactant with the environment that promote the reaction. In case of ASR, it's high temperature and maybe high alkaline solution. Here, Rodolfo has presented an example of chloride, but basically in any test that's developed, whether what Rodolfo has introduced or what I'm going to talk about today, it's all about taking that mechanism, mimic it in the lab, perhaps with accelerated conditions. So oxidation and sulfate attack, that's what we're trying to mimic. So Rodolfo also has presented what we included in the CSA in Annex P, which is the work that my colleagues at Laval University have produced, which is a protocol consisting of 3 tests. The first one is chemical test, total sulfur. Second one of is oxygen consumption. And then we have a mortar bar. And again, if I refer that to the mechanism, the first one, we're talking about the reactant. Is the reactant there or not? The sulfur and sulfide. Do we have enough of it? Number 2, focus on the first mechanism of the reaction. So the first one is the reactant. The second one is the oxidation. So we have aggregate, raw aggregate exposed to oxygen, and we see how much oxygen that aggregate can consume. If the aggregate has the high potential for oxidation, it will consume more oxygen and vice versa. And then the third one has the 2 mechanisms combined. It has the oxidation as well as the sulfate attack. So phase 1 focus on oxidation, phase 2 focus on sulfate attack. So the conditions are different. The first condition focus on oxidation. The second conditions or the conditions of the second phase focus on promoting sulfate attack. What I'm presenting today, and these are just the limit that was proposed by the Annex. So in the first stage of the mortar bar, which is the test that I'm focusing on now, but I'm also gonna move to another new test. The focus is on the second phase, which is the sulfate attack. So the requirement or the limit is a certain expansion limit in phase 2, for reasons that you were going that I'm going to present soon. So again, the focus is on the applicability of that protocol. The third test, the mortar bar, on 23 aggregates or 22 aggregates from Ontario and the lessons that we learn from there. And then the second part of the presentation is to have another or modify the test or come up with another test that can be used as a potential test for evaluating an aggregate and hopefully preventive measures if we're going to go in this direction. So we had around 22 aggregates we had 3 aggregates that are sulphide-bearing. Unfortunately, one of the drawbacks of the study here is we didn't have at that time enough sulphide-bearing aggregate. We couldn't allocate many sulphide-bearing aggregates. So what we did is we used the one from Trois-Rivières. We used one from Ontario, which has never been used in concrete, but it is known to have sulphide. And then we got an ore, a material that's considered as, of course, high potential for oxidation. It contains pyrite, peratite, many form of sulfide, and we use that ore as a source of sulfide. So we blended with non-reactive or non-sulfide aggregate just to see if the test is work, just to evaluate the test that we are developing. In addition to this 3 type of aggregate, we classify them as category 1, sulphide-bearing aggregate. We have other aggregates that are from different locations. Again, within Ontario. So category 1 is the sulfide base, as we said. Category 2 is carbonate aggregate. And then category 3 is non-carbonate aggregate. 2 and 3 are non-sulfide. The sulfur content are either low, or even if it's slightly high, the aggregates has excellent history of performance, no issue of sulfate attack. So again, we're just checking if the test work universally on these types of aggregates. So let's talk about the oxidation itself, or the test itself. It's not complicated, it's very simple. So basically what you see here is just the time and what we do during the test period. So phase 1 is the top bar, phase 2 is the bottom bar. Phase 1 focus on oxidation, and it's 2 cycles per week. So we soak the sample in bleach as an oxidizing agent, and then we expose it to high humidity, high heat. Then soak it again in bleach to get more oxidizing agent, and then expose it to high temperature and high relative humidity. Sorry, high temperature, high relative humidity. The whole idea is within the 13 weeks of phase 1, you promote oxidation and you get the oxidation product, namely sulfuric acid and gypsum. Then in stage 2, the condition will change because we are focusing on sulfate attack. The samples are, again, we soak them for 3 hours, and then they are exposed to 5 degrees Celsius and 100% humidity. This condition is to promote sulfate attack, namely thaumasite, simply because that aggregate, when my colleagues at Laval tested on site, they found that they produced, or the sulfate attack product was mainly in the form of thaumasite, or solid solution of thaumasite at Ettinger. So that's the test in a nutshell. So 2 cycles per week, the first 13 weeks for oxidation, 2 cycles per week, the last 13 weeks are for sulfate attack. Results, when we test for the carbonate aggregate, the test was found very suitable for carbonate aggregate. So if you look at the graph here, the solid bar represents phase 1, and then the dashed bar represent phase 2. The expansion limit is 0.1 in phase 2. So all the aggregate met the requirement, which is good. So the test is actually applicable to this group of aggregates, which is good. And then this type of aggregate is carbonate, but it has a little bit of silica. Not a little bit, actually it has around 20% of silica. And it has a total sulfur of 0.3. But the sulfur is not in the form of peratite. So we know that it is safe. When we looked at the sample after the exposure, we realized a little bit of reaction very similar to ASR because it has silica. The long exposure, 3 months in an alkaline solution, it's actually the bleach is also high. The bleach is high in pH. So it's roughly a relatively high alkaline solution and a very high temperature. You get a little bit of interaction with the silica, whether it's reactive or not. And that interaction might give you some expansion because, again, it's a very prolonged testing exposure. Moving to the non-carbonate aggregates, we got a little bit higher expansion. However, again, if you look at phase 2, all the expansion is less than 0.1. So the test is also applicable except for only one aggregate out of the 22, and which shows a little bit of high expansion or high expansion in phase 2. The aggregates, when we test them, those non-carbonate aggregates, when we test them for ASR 1260, they showed, particularly that one that has high expansion, it's actually showed ASR reactivity as well. But the most important thing is those who pass the ASR test at 14 days, when you leave them for 28 days, they start to show expansion. So that emphasizes that when you leave it at high temperature, some form of silica might become, you dissolve it, and that will actually produce expansion, which is not related to sulfide oxidation. So what is the conclusion? The conclusion is it works, the test works with the 0.1 limit so far based on that limited group of aggregates. However, because of this one, and even for the red one, the one with sulfide, perhaps one observation that you can see here is phase 2 compared to phase 1 for non-reactive or non-oxidizable is very small. If you look at the one with sulfide, even with this one here with sulfide, the ratio of phase 2 to phase 1 is much higher than what you get here. So our conclusion from this work, which is published in the ACI in 2020, is maybe instead of 0.1 expansion limit in phase 2, maybe a ratio of expansion in phase 2 divided by phase 1 can actually discriminate or can solve the issue of this aggregate, or if we have a category of aggregate that show high expansion in this test. Even ASR, if you look at an ASR aggregate, you will see very high expansion in phase 1. Once you move the aggregate to the 5 degrees Celsius, the slope of the curve will change dramatically. So if you take phase 2 divided by phase 1, it takes care of ASR or even non-ASR, but aggregate with high silica. Now we move to another form of test. Again, it's mortar bar, definitely as Rodolfo presented, or if you find from the conclusion, doing this on concrete because of the aggregate size will take longer time. So promoting the concrete to cause the oxidation and sulfate attack might take longer than mortar bar simply because of the size of the aggregate. So we're considering two types of tests here. Again, phase 1 and phase 2. Phase 1 oxidation, phase 2 sulfate attack. But we're trying two options. The first one with oxidizing agent, again, household bleach. The second one is just lime water or water saturated with lime. And the lime is there to just reduce leaching. We don't want to soak the mortar bar in fresh water. So it's lime saturated just to raise the pH to prevent leaching. So two conditions, one of them with bleach, the second one without bleach. What did we change here is instead of soaking the sample in bleach at high temperature, we soaked it at a normal temperature. So instead of 80 Celsius, only 23, just to mitigate that issue of silica dissolution at high temperature. The second one is natural. You're just changing the humidity. You're changing the, just drying and wetting our humidity to activate, allow oxygen to get in and get a little bit of oxidation. Within category 2 or option B, we tried different conditions as I'm going to present. So again, the bar chart is the same. So storage, this is the one with the bleach, but 23 and 70% humidity instead of 80-80. 23 and 70, and here 23, 70, the second phase, 5 degrees Celsius and 100% humidity. And then we looked at the expansion, and this was, the green one was the aggregate that show high expansion at high temperature. Now you can see that it's very flat, no oxidation. Here, the oxidation didn't seem to produce, we didn't see expansion due to oxidation. Keep in mind, this is small aggregate, it's crushed aggregate. When you get oxidation in a larger particle, you might see the expansion, but here we didn't see. But we saw the expansion associated with the second phase, which is exposure to sulfate attack. So this seems to be working. It's a good test. The only thing is the expansion is relatively low. We're able to get 0.06, 0.08. Yes, there is a clear discrimination between sulfide and non-sulfide aggregate, but I was hoping that this one will go a little bit on the high side. The second one is again, soaking in lime water. Now that we don't have bleach, I was more encouraged to raise the temperature. So we use the temperature of 40 degrees Celsius. And then the second phase, so this will be the first phase. And then we tried in the second phase to continue as is, assuming that at 40 degree and 100% humidity, or 40 degrees 70, you're likely to get both oxidation and sulfate attack. I want to draw your attention to something here, something very important. When you look at 70% humidity, it's in fact not 70, the minimum is 70. But because the exposure is pre-condition, there is a precondition of soaking, and because these are mortar bar, very small cross section, and because the water to cement ratio is relatively high, it's actually high, 0.65, it is very likely, or we actually tested, and the bar will get saturated in these 3 hours, or more or less very high degree of saturation. So the fact of the matter is, when you store it for 2.5 days or 2 days, the bar is actually start with a relative humidity of 100% and keep going down to 70, or maybe it will not reach 70. So you're actually testing the material at a range of relative humidity that start from 100 and can go down to close to 70, but not lower than 70. So at that relative humidity, I assume that you will have a little bit of oxygen penetration to get oxidation. I assume that you might get a little bit of ettringite or sulfate attack because of the high humidity and because of the soaking as well. So that's the same testing with phase 2. We didn't add anything. So basically phase 2, we store it here at 23. We tried 3 conditions. The storage, we tried in the second phase, we left it at 40 as is, or 40-70. The second condition is 100% humidity, but 23 Celsius. And the third one, 5 degrees Celsius. What is the difference? Some aggregate might, or it depends if you have carbonate or not. You might get ettringite, you might get thomsite. So when you test the same, not the same samples, you will make 6 bars. 3 bars will be tested at 23. 3 bars will be tested at 5. Depending on the aggregate, you might get more expansion at 23. For other aggregates, you might get more expansion at 5 degrees Celsius. And we run the test. So basically, this is the 3 conditions with Maskimo, the aggregate from Quebec. And we found that really at 5 degrees Celsius, you get the maximum, or thomsite is the dominant form of sulfate attack. So we continued, we run the test. And these are the results. Again, the siliceous aggregate or non-carbonate aggregate that used to show expansion, they are at the bottom here. What you see here is our Maskimo, the one from Trois-Rivières. And these are actually blended. So that's control aggregate, non-sulfide aggregate blended with the ore. Again, because of the lack of sulphide-bearing aggregate, we had to mix the ore with non-sulfide aggregate. So you can see there is a little bit, you can see a good discrimination here, high expansion in case of sulfide aggregate, non-sulfide, very low expansion. To me, the trouble is here. This one is marginal. So the 10% ore marginally fail, and I say marginally fail based on the oxygen consumption. If you remember me referring to that test. So this aggregate, that combination of aggregate consume 7.8% actually, 8% oxygen, which means it's on the high side, or it marginally failed the oxygen consumption. So I expect to see a little bit high expansion. I would be happier if that green line is actually here. But anyways, for Maskimo aggregate, there is still a discrimination between the sulfide and non-sulfide. Again, my same comment with the first test with the bleach, the expansion is relatively low. I was hoping to have high expansion, but nevertheless, it took care of some reactivity of silicate aggregate with the bleach, and it discriminated between the aggregate. If the expansion is high, it would have been much better. We did some SEM, and we found that the mechanism of damage is really sulfate attack. We're able to see either ettringite, as you can see, or solid solution of ettringite and thomsite. Same thing, we were able to see it with the Maskimo aggregate. So the previous one with the blend limestone and ore, here with Mascmo, and we were able to confirm that the expansion is really due to sulfate attack. With that, I hope I didn't take much time, but the conclusion is the current test, as stated in Annex B of CSA, does work. Perhaps with testing more aggregate, we might change, or there might be a need to change the expansion limit and use the ratio of phase 2 to phase 1. That conclusion is based on the suite of aggregate that I tested. With more testing coming, it might prove to be correct or not. We need to do more testing. And then the other mortar bar test in lime water shows clear discrimination between sulphide-bearing and non-sulphide-bearing aggregate. It's just the expansion was on the low side. I believe we need to test more aggregate before coming to a conclusion. When we test the aggregate, we tried the mortar bar, we tried 3 conditions. We suggest, or we recommend, testing at 5 degrees and 23, simply because you might have an aggregate, or you might have a condition that lead to yttrium more than thaumasite. And in another situation, you might have a condition leading to thaumasite, not yttrium. So the best way is to run the test at 5 degrees Celsius in phase 2, or 20 and 23 at the same time. So 6 bars, 3 here, 3 there, and get the maximum expansion as the indication of possible oxidation.